Good evening. Welcome back to AP Stats Notes Online. Got a couple of thoughts here to finish up, and then we'll be through section 10.1 and ready to start working towards a quiz. And able to move kind of quickly because we're just kind of doing the same thing over and over again, right? But some things to be aware of and make sure that you are, again, being very aware of what your situation's talking about so that you can make sure that your responses match to those situations, right? And here's what I mean. We have to be careful because most of the data that we've been working with have been coming from random samples. And so we know what to do with those. We know how to handle those. And we know what the language should be when we're looking at random samples. There are some very common mistakes that students make when we switch over and start talking about randomized experiments. And so we have to make sure that the language matches when we're talking about an experiment. And so what mistake do students often make when defining parameters in experiments, and how can you avoid it? Well, what happens more often than not is you kind of get stuck in this rut of your data coming from random samples, and so your language always refers to the sample, such as saying things like the proportion who took this, or the proportion of the people in the group, in the such and such group, right? And we don't want to do that. Mostly because when we're talking about randomizing into an experiment, randomizing into treatments, we can't talk about the population anymore, and we have to sort of hone in our parameters to just talking about people like those in the study, right? Because we can't generalize to the population anymore. So how do we fix that? Pretty simple. It's better to use present or future tense. And so I'll show you what I'm talking about here in just a second. Okay? So let's take a look at an example here. Right? And we're talking about, in an effort to reduce healthcare costs, GM sponsored a study to help employees stop smoking. In the study, half the subjects were randomly assigned to receive up to $750 for quitting smoking for a year, while the other half were simply encouraged to use traditional methods to stop smoking. None of the 878 volunteers knew that there was a financial incentive when they signed up. Okay? At the end of the year, 15% of those in the financial rewards group had quit smoking, while only 5% in the traditional group had quit smoking. Okay? Do the results of this study give convincing evidence that a financial incentive helps people quit smoking? Okay, and so the first common pitfall is stating your hypotheses and defining your parameters. And so here's the definition of the parameters that you want to use. Right, we're going to let P1 be the true quitting rate for employees like these who get a financial incentive to quit smoking. Right? What you don't want to say here, and where you get yourself in trouble, is saying that P1 is the true quitting rate for the employees in the financial incentive group. Okay? We want to make sure that we're not specifically talking about the group itself. We want to make sure that we're projecting this out into people like those in the group. Okay? And so we're going to have to continue to talk about this difference and make sure that we don't make that mistake. It would be a silly way to lose a point on the AP exam. And so trying to let you know kind of how picky they're going to be about this. But anyway, P1 is a true quitting rate for employees like these who get a financial incentive for quit smoking. P2 is the true quitting rate for employees like these who don't get a financial incentive to quit smoking. Okay? And now, we're going to test this at an alpha of 0.05. It's a pretty good default alpha level. And then our hypothesis should look something like this, right? Remember, the null hypothesis is that hypothesis of no difference. right? So if we're going to assume that there's no difference between the two types of incentive, then P1 should equal P2. What we're trying to find evidence for, and what we think might be happening, is it's in the question up here. The results of the study give convincing evidence that a financial incentive helps people quit smoking. So the financial incentive group, the proportion who quit smoking should be higher. At least that's what we're looking for. We're looking for evidence of that group being higher. And since that group is defined as the P1 group, then we're looking for P1 to be greater than P2. There have been a couple of questions about, does it matter how you define P1 and P2? Could you switch these? And the answer to that question is absolutely yes, you can switch those. There's nothing wrong with that. But if you do, you have to be careful and make sure that you switch the alternative hypothesis to say that P2 is greater than P1. And be aware of that, and when we get down to the conclude phase, be aware of that as well. Okay? All right. We need some conditions, and so we'll check those with the intent of doing a two-proportion z-test. Right? We've got two groups, and we assign to two groups, and we want to find the difference between those two groups. And so this is a two-proportion z-test. Okay? And so our conditions, random. The treatments were randomly assigned, or the subjects, all the subjects were randomly assigned to the two treatments. So we're good there. Normal. Now, here's the thing. Again, if we have an actual proportion to use, then that's what we would want to use in our normal condition check, but we don't. So we have to default back to the sample proportion, the p-hats. So the 439 times 0.15 and the 439 times 0.85 be for one group. And then you see there the 439 times 0.05 and the 439 times 0.95 for the other group. Same size, the 439, if you were curious, came from, since we're assigning 878 total volunteers, that's where the treatment group size came from. Okay? So we do all that, and all of those are bigger than 10. And so our individual sampling distributions for the P1 group and the P2 group are going to be approximately normal. Therefore, the combined sampling distribution is going to be approximately normal. Okay? Now, independent. The random assignment allows us to view these two groups as independent. We must assume that each employee's decision to quit is independent of other employees' decisions. See how the independent condition has changed. We're not assuming a certain population size. Okay? Here, and again, it's because we can't generalize to the population, we're not going to talk about the population here. This is an experiment. The best we can do is generalize to cause and effect. Make conclusions about cause and effect. Okay, so the independent condition does change. The verbiage here does change. We have to assume that each employee's decision to quit is independent of other employees' decisions. The random assignment allows us to see the two groups themselves as being independent, right? So there's kind of it's sort of a two-tier structure here. One, people in the financial incentive group will not influence whether or not the people in the other group are quitting, and vice versa. But then the people within the group, within each group, their decisions to quit need to be independent of anybody else's decisions. Okay? So again, the verbiage changes a little bit in your condition checks. So be careful with that. But those conditions check, and so we're ready to go ahead and do this. Do our test. We need a test statistic. I'm not ready to give up showing that work just yet. And so Z should come from, and so we're going to write this out. It should come from, what are we doing here? We're defining P1 being greater than P2, 15% quit in the financial rewards, and 5% quit in the encouragement group. Okay? We go do our z-score, so 0.15 minus 0.05 minus 0, right? We really don't need this last part, but I'll keep including it. That's what our claim is. And then where our standard deviation comes from, right? Remember, we're claiming, there's a claim that we're making that there's no difference. And so we need a combined proportion. Okay? So this is going to be a little tough. Okay? So, we have to pull our successes from our calculations in our normal check. So we've got 66 successes from the financial incentive group, and then 22 successes from the other group, and we're still going to divide that by our total of 878, right? And so when we do that, we get a pooled proportion of, do that real quick, about 10%, right? So now we're going to go 0.10 times 0.90 all over 439 plus 0.10 times 0.90 all over 439. Okay? And that will get you your 4.94. Okay? Now, you can go use normal CDF. You can go into Table A and look up the probability of your difference being this far from the claim, 4.94 standard deviations above the claim. Or you can use some common sense and recognize that we're almost 5 standard deviations, this difference is almost 5 standard deviations above the claim of 0 difference. And so our p-value will indeed end up being pretty close to 0. As a matter of fact, when we type this into our calculator to do our test, we'll see that as well. So our p-value is about 0. Great. What does this mean? And that we get into our conclusion. First off, the first sentence has to be about h-naught. Since the p-value is less than 0.05, we reject h-naught. Second sentence has to deal with what does that mean in context of our test. That means that we have convincing evidence that financial incentives help employees like these quit smoking. And you have to include this. Remember, we're not generalizing to the entire population. And so we're limited. Our scope here is limited to employees like the ones in the experiment. And so make sure that you're including that little phrase in there. And it's the same when you're defining your parameters. You have to make everyone aware that you understand that we're not trying to generalize this to the population. We're only trying to find cause and effect, and it only applies for people that are like the ones that are in our study, that are in our experiment. So make sure you're including those phrases. Okay? But that's it. There you go. A significance test involving the use of data from a randomized experiment. And again, the verbiage, the language does change a little bit, and so you have to be very aware about where your data is coming from and how that affects your condition checks and the way you define your parameters and even the way you conclude your tests. Okay? So do be careful there. But that's it. That's all I wanted to show you there. You obviously can do the significance test in your calculator. I don't know if it's of any value to use time either in the notes or in class to show you that. I'll ask in class if anybody wants to walk through it. If not, you guys are getting pretty good about figuring out where those functions are in your calculator, and then the calculator is pretty straightforward as far as what it wants you to include. Okay? Okay, so that's it for section 10.1. We'll start working towards the quiz. Have a good night, and we'll see you guys in the next class.